Today we come to chapter 10, temperature and heat. First, let's review the three temperature scales. We have learned temperature in Celsius, it's symbolized by TC and using the Celsius degree as a unit. We also learned Fahrenheit. Normally I use TF and it's Fahrenheit degree. And also learned absolute scale. Or sometimes called Kelvin scale. That's actually normally just use a T or sometimes use TK. Anyway, I use TK. K means Kelvin scale and it has a unit Kelvin. The same as this one, but I just use letter K for Kelvin. We need to know the conversions between the three temperature scales. Okay, so the first conversion from Fahrenheit, Celsius to Fahrenheit is 9/5 times the temperature in Celsius plus 32 degrees. You convert the Celsius to Fahrenheit. The second equation, actually the relation between the absolute scale and the Celsius is simply the Celsius degree plus 273.15. That's a number make absolute temperature if the TC reaching minus 273.15 Celsius degree. So absolute zero means the Kelvin scale temperature is zero. So that's the lower limit for the whole universe. You can never reach or produce a temperature equal to zero or below 0K. Now, second, we introduce heat. Normally use letter Q to express heat. The heat has two units. One is calorie, the other is joule. CL or J. You have noticed joule is actually the unit of energy. So heat is actually energy. If you have an object that has a mass m in gram, today we use gram for the unit, and it has the initial temperature Ti, and then you warm it up, supply the heat. The temperature is going to go up to TF. Then there's the equation to describe this process. The heat required to warm up that much of a substance from temperature Ti to TF is equal to a constant C times the mass of the substance and times the temperature change of the substance. The C number is called specific heat capacity. It has a unit calorie per gram per Celsius degree. You can also use another unit like SI unit. well, it would be joule per kilogram per Kelvin. Anyway, we're going to use calorie gram per gram Celsius degree more often. Now, specific heat capacity is a constant for different substance. For example, for water, it's exactly 1.0 calorie per gram Celsius degree. For aluminum, it's about 0.22 calorie per gram Celsius degree. Now we come to the third point. It's work done by the gas under constant pressure, P. So over here I have a diagram showing a certain amount of gas enclosed in a container, enclosed by actually a piston. That's a piston. Then if the heat flowing into the system, the gas will expand and push the piston out and do the work. So this is the one piston, just initial state and the final state. It was pushed out to do the work. This is actually a very simple model of engine. All the engines have such a structure, some gas inside, and be heated up and push the piston to do the work. So the equation for the work done by the gas is the work done by the gas equal to the pressure, which is a constant in the container, times the volume change of the gas. So the initial one of the gas I marked as V1, that's cubic meter. And then after expansion, the piston was pushed out and given the second volume, which is after doing the work, that's V2. So V1 refers to the volume of that much. V2 refers to the volume after expansion, that's the whole part, including that part. So the equation to do for the work done by the gas is the pressure times the volume change. Over here, you have noticed that it's not the velocity, it's the volume change. It's the initial volume of the gas and the final one of the gas after expansion. You should notice the pressure over here is in a constant pressure. Sometimes if the pressure is not a constant, you cannot directly use that equation, but that's a little advanced physics. We'll not discuss that here. Now the fourth point is first law of thermodynamics. So the first law of thermodynamics talks about internal energy change delta U of the gas in that thermodynamic system or any thermodynamic system. I just take this as example. That means if the heat flows in, the gas expanding to the work. Meanwhile, the gas will increase its temperature. Then the internal energy of the gas will change. So the internal energy change described by the first law of thermodynamics, formalized by that equation, is equal to the heat flowing into the system minus work done by the gas. This is the first law of thermodynamics. You should pay attention to the units. The internal energy has a unit of joule. The work done by the gas has a unit of joule. But the heat, it has two different units. Sometimes we use calorie, sometimes we use joule. So 1 calorie equal to 4.19 joule, that's the equivalent factor. Sometimes we approximate to rounded to 4.2 joule. Let's give example. Suppose the heat flowing into the system is 1,000 calorie and the work done by the gas is 2,000 joule. Then how to calculate the internal energy change of the gas? According to the first law of thermodynamics, is equal to the heat minus the work. So you might want to use 1,000 calorie minus 2,000 joule. However, you could not do so because they have different unit. So you have to do the conversion. The internal energy change equal to the heat minus the work done by the gas equal to 1,000 calorie times 4.2 joule per calorie. Then you convert that into joule minus 2,000 joule. Then the all units are joules. You are able to do the calculation. So you got 4,200 joule for the heat minus 2,000 joule work. You got 2,200 joule for the internal energy change. So you should pay attention to that unit conversion.